Chapter 5. The 5 Coherent Bases and Limits in the Constants of Nature. At the end of Chapter 3, we stood surrounded by data, 288 constants, each a fingerprint pressed into the fabric of reality. These constants define how particles interact, how forces propagate, how time evolves. Together, they form the silent symphony of atomic structure. But where do these constants come from? Why do they take on the values they do? Why is the speed of light what it is and not double or half? Why does the electron have the mass it does? Why does the fine structure constant have its precise value? These are questions that haunt anyone that has discovered these built-in features of the world. Because while our best theories require these constants in order to work, they offer no insight into where the constants themselves originate. We measure them, which means we can report them to only the accuracy of our measurements. We use them in our equations, but we have no understanding of their origins. Some constants describe coupling strengths, others describe masses, momentum, or energies. Some have dimensions, others are dimensionless. Some appear in classical mechanics, others only in the quantum realm. What unites them is they are all empirical, known only for measurement. At its best, physics is a discipline of explanation. It seeks to reduce the arbitrary to the necessary. It looks for unity beneath complexity. And so, the constants of nature stand as both triumph and limitation. They let us model the world with astonishing accuracy, but they also reveal the limits of our understanding. If a theory of everything is to exist, then it must explain the constants of nature. It must show why they take the values they do, and not others, and it must do so from principles more basic than the constants themselves. It must render them inevitable. The constants of nature cannot remain brute facts. They must become consequences, results of something deeper, something structural, something geometric, something that persists. When one takes up the task of making sense of the constants of nature, examining them all, one by one, the first thing you notice is that the constants of nature all form a conversation about the 5 bases of atomic logic, and the boundaries of those bases. In other words, the constants of nature unmistakably encode the 5 coherent bases of atomic logic: the second, meter, Coulomb, Kelvin, and kilogram, and they encode the boundaries of those bases: the Planck time, Planck length, Planck charge, Planck temperature, and Planck mass. To see at a glance what I mean, the Planck constant divided by the Hertz-Joule relationship is equal to 1 second, exactly. Since our highest precision measurements approach 14 significant digits of accuracy, we will call a 14-digit match exact, meaning as matched as can be checked against. Here are several examples of simple combinations of constants of nature that precisely encode one of the bases of atomic logic. Planck constant divided by the Hertz-Joule relationship gives us exactly 1 second. The conventional value of Coulomb 90 divided by the conventional value of Ampere 90 gives us exactly 1 second. Conventional value of Henry 90 divided by conventional value of Ohm 90 gives us exactly 1 second, and on down the list. This isn't coincidence. Nature is built from these atomic bases. Its logic is structured by these bases into a coherent geometric language. The rest of this book will uncover what that language is. There are also combinations of constants in nature that encode the atomic bases, but notably only to roughly half the precision. For example, the speed of light divided by the Hertz inverse meter relationship gives us 0.99999992995 seconds. Scroll on down, another example here. W90 over V90 gives us 1.0000000888706 coulombs. The constants of nature encode the SI bases of units because these are the coherent atomic bases. Some combine to characterize those bases to all 14 digits, others to roughly 7. This is our first hint at some kind of two-part structure in the connective logic of atoms. Newton's theory already had the precision of something like 1 part in 10 to the 7, and then Einstein comes along and produces a theory which is now known to have a precision something like 1 part in 10 to the 14, Roger Penrose. To find the pattern in a complex set of data, it is often useful to reduce the complexity of what you're looking at. In a data set with many different dimensions, one way of reducing complexity is to look at all the ways we can combine different constants of nature, multiply or divide them, to yield an output with only a single dimension. When we do this, we may find we've singled out a coherent base of atomic logic, second, meter, coulomb, Kelvin, kilogram, or one of the mysterious boundaries to those bases, a Planck constant, the Planck time, the Planck length, Planck charge, Planck temperature, and Planck mass. Here are some combinations of constants of nature that encode those boundaries to roughly 7 digits of precision. Let's notice in here we have 2 different ways of defining, say, the Planck charge boundary, different arrangements of constants, and they both agree for the first 1, 2, 3, 4, 5, 6, 7, 8 digits, right? And then they're different. Here again, even when talking about the boundaries to those bases instead of the bases themselves, we find a combinatorial structure in the constants of nature, one that appears 2-part, with a clean division between high precision and half precision characterizations. These Planck constants point us toward a hidden architecture. They are not mere conveniences. They are natural boundaries responsible for the constructive logic of atoms. They define the smallest possible amount of time in that logical system, the shortest possible length, the strongest possible charge, the hottest possible temperature, and the largest possible mass that maintains the construction of the coherent system. Together, the constants of nature form a conversation about the 5 coherent bases of atomic logic, second, meter, coulomb, Kelvin, kilogram, maintained by the 5 Planck boundaries. This is why physicists call the second, meter, coulomb, Kelvin, and kilogram the coherent bases of atomic logic. They are woven into the logic of physical law. It is also why they call the Planck constants natural units. The trouble with trying to construct a world with Planck constants is that we only know them to a few significant digits. This precision limit isn't due to poor instruments. It's built in. When we report a Planck value, we're really reporting a band, a narrow spectrum of what remains after the noise is cleared. What if that ambiguity is a clue? The Planck constants are extracted from the constants of nature. There are several ways to combine different sets of constants to reduce to a single-dimensional expression, resolving the inbuilt boundary of that dimension. But when we do this, we get the same number for about the first 7 digits, and then we get divergence. When we report the value of the Planck constants, we are reporting the range of values this search yields. To construct a world from Planck constants, we need exact geometric definitions for them, not as products of empirical constants, but as structural features of a deeper space, a space with rules, symmetries, and boundaries of its own, a space in which persistence is possible, and from which all the constants naturally emerge as expressions of how that persistence is structured. That became the quest. To define the Planck constants geometrically, to derive the constants of nature not from experiments alone, but from the very logic of the arena they occur in, to discover what reality must be like for these constants to be inevitable. Chapter 6. Algebraic Descent into Bipart Structure. For years, from waking to sleep, I asked the same question in thousands of forms. What do the constants of nature say to each other? Using dimensional analysis, ratios, powers, logarithms, and the help of Wolfram Alpha, I compared every constant with every other, relentlessly seeking echoes of order. I followed every numerical shadow and whisper. I was looking not just for patterns, but for reasons. Eventually, a pattern began to emerge, but it came with a mystery. No matter which value I used for the Planck constants, constructing constants of nature from them always hit the same agreement limit, 7 digits. Beyond that, the numbers diverged. What explains this divergence? It is loosely said that we extract the Planck length and the Planck time, things we only know to roughly 7 significant digits, from the speed of light. But this is an oversimplification. This is made evident from the fact that the speed of light is known to 10 significant digits. We only claim 7 digits for the Planck time and Planck length because we extract them from many possible arrangements of constants. The spread in those values defines their uncertainty, and that uncertainty reveals a constructive feature, a rule for how Planck boundaries construct. This constructive feature is responsible for blurring their precision beyond 7 digits. As we practice building the constants of nature from Planck constants, we discover that no matter what number we use for them, this changing of the guard in how things work always occurs around the 7th digit. This constructive feature can't be normalized out. Why? Clearly, the constants of nature are telling us that they define a system that is two-part, and the second part is much smaller than the first, showing up only around the half-precision point. The best measurements we have for any constant of nature approaches 14 significant digits. If 14 digits represents a precision limit, then perhaps something else comes into play at halfway. 7 digits of agreement is not a coincidence. It's an invitation to look closer. If the atomic bases and the Planck constants are derived from many different combinations of constants of nature, and all of them agree to about 7 digits, but then disagree, then something else intervenes at this scale, something not yet understood. In effect, the constants of nature are whispering, "You're missing something." When building a universe from Planck constants, there's a second layer, made by the Planck constants themselves. And then something clicked. I had previously noticed that a very specific combination of Planck constants, the product of the Planck length and Planck mass divided by the Planck charge squared, yielded a magnitude surprisingly close to the value of that 7th digit. That was the scale of deviation, the second term in a structure that only begins to manifest in the 7th digit. The constants were behaving like dual structures, with a dominant expression and a subtle correction. That idea lit a fuse. The Planck constants weren't just quantities, they were modular constraints, and the 7-digit threshold was a crossover point where another rule began to assert itself. The constants were speaking in pairs. No matter how I approached them, no matter which set of Planck boundaries I used, the same pattern emerged. Each constant seemed to resolve into a dominant structure and a subtle correction, 2 expressions layered into one. It was as if each constant of nature had been woven from 2 threads, an external action composed from an arrangement of Planck boundaries, and an internal counterpart, an embedded inversion term that began to assert itself at the 7th digit. These were not small corrections, they were essential. Each constant encodes a pairing, a kind of algebraic dialogue between what is externally arranged and what is internally required. Writing down that structural relationship gives us the binomial constructor, where A external is the geometric action applied to the external arrangement of Planck boundaries, B external, and A internal is a second geometric action applied to the system's internal inversion boundary. Similar to how the binomial theorem captures the logic of expansion in algebra, revealing how a whole can be decomposed into all its pairwise interactions, our binomial constructor captures the structural logic by which the constants of nature emerge, each being a precise balance of 2 geometric layers, each necessary, each encoded in the language of Planck boundaries. If we had geometric definitions for the Planck constants, if we knew them precisely, then this constraint of binomial construction would give us a way to pull apart every single constant of nature in terms of its external and internal geometric arrangements of Planck boundaries. But without precise definitions for the Planck constants, the power of this decoder must wait.